Hello everyone, welcome to another video of statistical mechanics. And here we'll be discussing this is the last topic of canonical ensemble. We have been doing canonical ensemble, and this this topic that we will do today is it's called quantum dipoles. We did classical dipoles in the previous one. This is a quantum dipoles. Okay, so what is a quantum dipole? For example, the system is like this. There are n dipoles oriented very randomly. Okay, so partition function for the whole system will be what? Partition function for the whole sorry the whole system. Zn is equal to z1 to the power n, right? Hmm? So again we have to focus on z1, right? Because we have to because z1 is a what for a single dipole, and we have to find for n dipoles. For that we need to first calculate for single dipole, that is z1. Okay, so our magnetic dipole is placed in what? Again, I have told you the magnetic field direction is should be always be z cap, right? So our magnetic dipole is placed in this magnetic field. Hmm. So as this is a quantum dipole, what will happen? These dipoles will orient in some particular orientation. It will not be continuous orientation like classical dipoles. Okay, sorry classical dipoles will orient in continuous directions, continuous orientations. But your quantum dipoles will orient in what? In a discrete orientation. Discrete means particular orientations. Okay, this is not continuous. Is it all right? Yeah. So now your mu z will be what? Suppose this is your mu. This is a theta. So mu z will be mu cos theta, isn't it? Mu cos theta. So how many orientations are possible? First of all, if you see mu z, this is mu z. Mu z is equal to mu cos theta, right? Sorry. Mu z is equal to mu cos theta. So your cos theta is equal to how much? Mu z divided by mu. Is that all right? So from quantum mechanics, we know that. We know what? We know mu is equal to Gj E by 2m J cap. Okay, this is a magnetic dipole moment. So G where Gj is what? Gj is Landage factor. Gj is Landage factor. And what is the value for Landage factor? Gj is equal to 1 plus. You would have studied it in atomic and molecular physics. S all into S plus 1 minus L into L plus 1 whole divided by 2j plus 1. Okay. So Gj E by 2m. This is called what? This is called gyromagnetic ratio. Okay. This is called gyromagnetic ratio, which is a what? Mu by J. Mu by J. Yeah. So now your we know mu I just wrote mu is equal to, so mu, if I write Gj by Gj E by 2m into J vector, if I take the magnitude is equal to Gj E by 2m, what is the J vector magnitude? J vector magnitude is root over of J whole into J plus 1 and H cut, because J is actually what? J square is what? J whole into J plus 1 H cut square. So J is equal to root over of J whole into J plus 1 H cut. Okay, so mu vector magnitude is equal to Gj E by 2m root over of J whole into J plus 1 H cut. Is that alright? Okay. Yeah. So uh, here what will happen? Here we know it is mu z, right? Mu z will be what? Gj E by 2m, and the J orientation will be also along Z direction, same as mu. Alright. And see, and Jz I can write what? MJH cut. We know that. Okay, JZ is MJH cut. So write down GJ E by 2m, E by 2m, M, sorry, there is some problem, MJH cut. Okay, and MJ has how many values? If you see, MJ has how many values? MJ has values from minus J to plus J, right? MJ has values from minus J to J plus J. That means 2J plus 1 values. 2J plus 1 values. MJ has 2J plus 1 values. Okay. So the orientations would be how much? See, orientation cos theta was how much? Mu divided by mu z divided by mu. So mu z is your what? Gj E by 2m jz whole divided by this one Gj E by 2m root over of j whole into j plus 1 h cut. This is exactly what I did. Okay, this is exactly, see, mu is this. I put it here in place of mu, and mu z is this. I put it here. Got it? Is it all right? Mu z is this one. Okay. So Gj by 2 and Gj by 2 m cancelled out. So this is now what? Jz by, okay, Jz is a what? Mjh cut. Mjh cut divided by root over of j whole into j plus 1 h cut. So h cut cancelled out, and that will be mj divided by root over of j plus j plus 1. Okay. So this is a what? Cos theta. This is a cos theta. So theta, orientation theta is equal to what? Cos inverse mj divided by j whole into j plus 1. So if you see, this is actually discrete, isn't it? This is not continuous. Okay, because j has a particular value, that is mj has a particular value, that is plus j to minus j, right? Yeah, yeah. Okay. So our energy value is what? Energy value is minus mu dot b. Okay. So minus mu z bz. Hmm. And mu z is what? Just a second. Mu z is what? Mu z is gj e by 2m mj cut. Okay, is it all right? So I can put this value here. So E is equal to minus Gj V by 2m. Okay, I can write this also as minus Gj mu B mj B. Why? Because Eh cut by 2m is written as mu B, that is Bohr magneton. Okay, this is the energy. Okay, so this is the energy value. This is all right. Now, why did I do this energy thing? What was the need of getting energy? Because we need to calculate partition function for a single system, right? So partition function needs your energy value, isn't it? Partition function needs your energy value because Z is equal to what? Summation I gi e to the power minus beta I, isn't it? So energy value we obviously need it. So this is mj is equal to minus j to j gi energy value e to the minus beta minus gj mu b mj b. Okay, so if you just make the minus minus plus, and d genesis is one on like generally, so mj minus j to j e to the power beta gj mu b mjb. Okay, yeah. For example, this is a alpha. Okay, um, yeah, I think we should just keep it this much. Okay, this will be a partition function. Don't need to remember it actually. You can just leave it here. Okay, and the values that will be given, you just have to put it here. All right. Yeah. Okay. How will the questions come from this part? How will the question will be like, the language of the question, the language of the problem will contain, we have in spinor particles. Okay, in magnetic field, and j is equal to half case. This is j is equal to half case. Um, so see, system is already mentioned. Spinor particles, right? Already mentioned. Hmm. And to study the system, we have to first what? Find partition function. Since they are distinguishable, so Zn is equal to Z1 to the power n, isn't it? So ultimately, we have to focus on Z1, right? So again, it will have discrete orientations, isn't it? Discrete orientations, and from that, if we do cos theta, here will be what? See, here S value is given. So S is equal to half. S value is given. S spin half. So S is equal to half. So for that, I will write what here? I will write ms divided by root over of s whole into s plus 1. How did this come? How did this come? Cos theta is equal to mu z by mu. Okay, mu z is what? If you do all the G S mu B ms h cut divided by G S mu B root over of s whole into s plus 1 h cut. So this h cut cancelled, mu b, g s cancelled. So what is left? Ms by root over of s whole into s plus 1, where ms is equal to what? Magnetic spin quantum number. Magnetic spin quantum number. Okay, magnetic spin quantum number. And what are the values of ms? Ms values are minus s to plus s. These are the ms values. Okay, in integral spins. Is it all right? Yeah. So there will be 2s plus 1 values. So theta is what exactly? Theta is cos inverse ms by root over of s whole into s plus 1. Okay. And yeah. So there are 2s plus 1 orientations. Okay. Here spin is half. So spin is half means 2 into half plus 1 orientation. That means two orientations will be there. How will be the two orientations? Ms will be how much? Plus half is one orientation, another orientation is minus half, because two orientations are. So plus half and minus half. Okay. So for plus half, the arrangement will be like this. The orientation will be like this: one here, one here. Okay. This will be a theta one. This will be a theta two. All right. This will be a what? Plus half h cut. This will be a minus half h cut. If you see, this is your up spin. This part is your up spin. Okay. This is your down spin, and this will precise. This is called precision motion. It will precise like this. All right. Yeah. This is, you must have studied this in atomic physics. Okay, vector atomic model and all. Okay, next is your interaction energy. Okay, what is the interaction energy of a dipole? Interaction energy. Interaction energy of a dipole with magnetic field. With magnetic field. Okay, interaction energy of a dipole with magnetic field P E, interaction energy, is equal to mu dot B. That is mu z b z. Okay, mu z b z. All right. And E is what? Energy is what? Minus mu dot B. So here we can write minus mu zb, okay, or bz, whatever. All right. So if you see, E will have two values. One will be minus mu bb, another will be plus mu b. You can write it as mu b like that. Minus mu bb plus mu bb. Right. So two values for E. This one is for, okay, minus mu dot b or mu b dot b, whatever. So this one is for parallel orientation. Okay, spin is along the magnetic field direction. Then minus mu b cos theta is 1. Then this will become minus. So parallel orientation of spin along the magnetic field. This is for anti-parallel. Like this is in the spin is in this direction, magnetic field in this direction, or spin is down and magnetic field is up. So this is for this one, the opposite orientation. Okay, anti-parallel or opposite orientation, anti-parallel orientation of spin. Hmm. Anti-parallel orientation. Okay, so two values of E we got. So now energy, if we got the energy value, then only we can get the partition function. That will be what? Summation I gi e to the power minus beta ei. So that will be what? E to the power minus beta minus mu b. Okay, mu b b, whatever, plus e to the power minus beta mu b b. Okay, so that will be e to the power beta mu b b plus e to the power minus beta mu b. Okay, is it all right? So z1 will be, if you see, this is what exactly? E to the power x plus e to the power minus x by 2 is a what? Cos hyperbolic x. So this is what? If I divided 2, multiply 2, if I divided 2 and multiply 2, this is Cos hyperbolic. So 2 cos hyperbolic beta mu b b. Is it all right? So this is for a single particle. For n particles, Zn is equal to Z1 to the power n. That will be 2 cos hyperbolic beta mu b b to the power n. Okay, isn't it? That's it. Okay, this is a partition function. Internal energy will be same process we are doing, just doing it again and again for different, but for different systems we are trying to do. Okay, minus del by del beta of ln z. So minus del by del beta of ln 2 cos hyperbolic beta mu b b to the power n. So n is here exponent, it will come down. So minus n del by del beta of ln 2 cos hyperbolic beta mu b b. Is it all right? Now I'll take the derivative of it, minus n into 1 by 2 cos hyperbolic. What happened? Sorry. 2 1 by 2 cos hyperbolic beta mu b b, and the derivative of 2 cos is 2 sine hyperbolic. There is no negative in hyperbolic functions differentiation. Okay, into mu b b. All right, is it all right? So 2 cancel out. This is actually cot. So minus n mu b b cot hyperbolic meta mu b b. Is it all right? So this is your what? This is your uh, internal energy. Okay, this is a what? This is your internal energy. Now this same way you can calculate Helmholtz free energy, that is minus KTLN Z. Just put the value of Z and everything else. The pressure will be minus del A by del V. Okay, NT constant, and chemical potential del A by del N, and your Vt constant, entropy S is equal to minus del A by del T, and your NV constant. So these are some of the things you can calculate, I hope. All right. Yeah. So this is your part of your what? Quantum dipoles. Okay. So classical dipole we did in the previous class. This is the session for quantum dipoles. Is it all right? Is it clear to everyone? Okay. Yeah. All right. Okay. This was a short session because now your canonical ensemble is finished. Okay. This is the most important topic in any entrance exam. Canonical ensemble. This is over. Done. Okay, canonical ensemble is over. We did everything numerical type. Like these questions are actually numerical based, isn't it? I taught you through theory, but these are numericals only. Okay, and I hope you learned something in these sessions. Okay, next session will be your completely one session will be required for your grand canonical ensemble. Next session will be your, I don't want to mix it here. Grand canonical. That's why I wanted to just take a short session and finish the canonical ensemble. After that, we will study Ising model, which is most important for CSR net and GATE also. Okay, Ising model. I think Ising model is also very important, very interesting and easy. It's not hard. And the final one will be your quantum statistics. And then your statistical mechanics will be kind of over for your syllabus. Like your syllabus will be over. Okay, it's not like it will be over. It's a very large domain of physics. It will never be over. Anyway, so these things, three things are left in statistical mechanics, which we will of course finish it. Otherwise, we have almost covered everything. And yeah, one class I will take for random walk problem, which I haven't taken. Yeah, because it's easy. It's easy. We'll do it at class. Random walk, like problem or whatever, random walk model, whatever. So these four things are left in statistical mechanics. After which we will have some grasp of statistical mechanics, like at least some graphs, like 5% or 10%, I would say only 5 to 10% only. This is nothing else. Whatever we have studied so far is nothing else. This is just a drop. This is just a drop in the ocean called statistical mechanics. Okay, we have to learn a lot. We have to go a lot deeper than this. This is only a overview. This is only a overview of what lies beneath it. Okay, and yeah, we'll be trying to solve more questions from. I will recommend you to read R.K. Patharia. Okay, those who are actually doing MSc right now should read this book. Those who are actually in the BSc can try, but they don't need to go that much. But they can try. They can read, no problem. Otherwise, MSc people should read R.K. Patharia. Yeah, it's a bit difficult, but you should read it. At a little, it will give you some clearance and some depth. You may not understand everything, but that's okay. And we'll be solving questions from Patharia after all this is over. And yeah, statistics. See, my I will tell you my plan. My plan in this channel will be to mainly focus on quantum mechanics, statistical mechanics. Like in the next few months, my plan, few months or days or whatever, quantum mechanics, statistical mechanics. There is another sub region of this is atomic and molecular physics, which I want to try. I will try to go a bit deeper in this field because this is a field. Atomic molecular is kind of a research oriented field, so we have to go a bit deeper in it. Okay, and particle physics. Particle physics is like a very we need a more depth in this. Okay, we need to have more sessions on particle physics, not from exam point of view, from a point of view of research and for your PhD interviews, and we have to go a bit deeper into particle physics. And for particle physics to go to that level, we need to have a clear understanding of quantum mechanics. Okay, and yeah, we need to really have a clear understanding of quantum mechanics. So these are some. I will mainly focus on these three things from like in this next few months of this thing. And other things, see, other things you can handle. Other things are for exam oriented, like classical mechanics. If you take classical mechanics, that is purely purely exam based. And the classical mechanics is something I will not be doing in this channel. Okay, this is something I myself, I shouldn't say this, but I myself am not interested in. So I won't be doing classical mechanics in this channel, and we will be doing mathematical physics whenever I feel like that we need to do it. Mathematical physics is also very important for undergrad students, for students like BSc and MSc students. Okay, this is also very mark fetching in entrance exams, but you need to have again clarity in mathematical physics to go higher in quantum mechanics and all. And yeah, we'll be so yeah. Another topic I forgot. How can I forget? Electromagnetism. It's something. Yeah, I have done a lot of videos on electromagnetism. Like we have tried to solve Griffith. So yeah, of course. But now quantum and statistical are going. So I'm not. I've just kept it aside. But we'll be also solving electromagnetism because it's also very interesting. Electromagnetism is also something I really am fascinated in. So I'll be doing that also. These four and five will be my main focus in this channel. I'm just making clear too. And mathematical physics is actually basically it's only mathematics is there, right? Mathematics. So we have so that will be we'll be doing during exam times. Okay, and it's not like you need a lot of explanation for it. This is only purely mathematics, which you just need practice. You just need practice for mathematical physics, and this is just for exam. You won't be asked questions from this in interviews or something. Yeah, you may be asked about applications of it, so you need to read for that. Yeah, I was saying classical mechanics is something I'm not interested in, so I won't be making videos on it. Suppose you must be wondering if I'm going to do videos. No, I'm not going to do videos on classical mechanics. And electronics I will be doing after this, like quantum and statistical are over. If they won't be over, quantum statistical will go on as long as my channel is there. It will go on. Like you may be feeling like now the syllabus is over. That the syllabus is never over for quantum mechanics and statistical mechanics. We can always go a bit deeper. For example, we just solved Jet Li. For example, we took 1 year and solved the whole Jet Li. Now we should pick up another book. We should pick up another book like Griffith and try to solve it. After Griffith is over, we should pick another foreign author book and try to solve it. Again, statistical, if we finished R.K. Patharia in 1 year, suppose, in 2025 we finished, by 2025 we finished R.K. Patharia. So it's not like we're done with. We should pick up another harder book and try to solve it. So as long as we're solving questions and reading books, our touch will be there. Our depth will keep on increasing. So that's the main funda of this channel is to increase the grow our depth in physics, not to just like reading it for reading's sake or exam's sake. We need to understand it. We need to have a depth for which we'll be able to crack interviews. Interviews can only be cracked if you have depth. If you don't have depth, you cannot crack interviews. You will stop at a point. You may answer 2 or 3 questions, but after that, when they ask you why this, why that, why not this, why didn't you think this way, then your mouth will stop answering. You will be stuck there, and you'll be thinking why I didn't think this way. So that's a very important thing. For that, we need to read more books. We need to read in such a way that we gain more depth in the subject. Okay. Okay, so that's the plan here. Electronics, yeah, I will be doing also. We will be only solving numericals. Okay, I won't be going into theory of it because I will agree. I will say electronics is also not my strongest part. So I will only do numericals of selected topics that I myself prepared for my exam. Yeah. So yeah, this is the a plan right now, and I will be doing according to it. Yeah, and yeah, this is the plan for higher studies videos, like videos related to MSc or your gate or net or JEST. Okay, these are related to this, and other videos for like 12th class videos. This is that would be for that is separate section. Okay, yeah. So I will recommend you to read R.K. Patharia. I will recommend you to solve questions on your own. Whatever we have studied before, we have studied can we have finished canonical ensemble from a point. And I hope you read books. You try to solve questions. If you have any doubts, please let me know in the Telegram. And my I will be giving my I have given my Telegram channel link a lot of times, so you can join it if you want. Okay. Thank you for watching, and yeah.